So the XRR scans are collected at very low incident reflected angles. They're almost parallel to the sample surface, but that's hard to draw. So these schematic angles are exaggerated just for clarity. So again, we have the center of the axis. The entire incident side arm is now rotated up omega, and the entire receiving arm is rotated up in 2 theta. So you can see how the motion goes. And both of those are in motion for a 2 theta omega XRR scan. So what happens during the scan? Every material has its own critical angle, and that's an angle at which, if at higher incident angle, the X-rays are no longer completely externally reflected from the surface. They actually start to refract from the material. So on the lower left is a case where the incident angle is lower, less than the critical angle. And so the beam in red is completely reflected from the surface. In the scan, you see some of the direct beam, but you don't see anything else. Everything else is reflection. Now the x-axis in this case is 2 theta. It's a 2 theta omega scan. We use 2 theta for the axis. Intensity scale is logarithmic because the intensity difference between the highest intensity and lowest intensity is several orders of magnitude. In the center case, we've reached the critical angle. So the incident angle is exactly at the critical angle. And in addition to the reflected beam, we can also see that part of the beam is now traveling along the top surface of the sample. In the scan, that's a point at which the scan intensity will start to drop. And that's how we normally find the critical angle of a material. On the right is the case of every angle that's above that. And usually for incident angle, we go up to as high as 5 degrees, whereas critical angles are something like half a degree. So on the right case, where we're above the critical angle, we can see that we're reflecting, refracting, sometimes transmitting part of the beam. And because it's insensitive to changes in electron density across interfaces, the interface in one direction and the interface in the other direction have the same interactions. So it's a very complex interaction. But from the constructive interference of these waves, we get the actual fringes and the scan intensity that we can then analyze. In the plot that you see, past the critical angle, there are 4 main Kaisig fringes. Kaisig fringes are spaced such that the thicker the film, the closer together the fringes are, the narrower the spacing. And so something like this would have a thickness of something on like 40, 50 nanometers, something along those lines.